Hello, and welcome to QuantPy. As the merchant, Vasicek, and CIO tools produce similar analysis, we use Vasicek model to demonstrate all these tools. Let's assume that the current value of the instantaneous short rate is 1%, its long-run mean is 5%, its mean reversion speed is 0.1, and it has a volatility of 1%. In simple terms, it means that the short rate starts at 1%, moves over time in some random fashion, with the scale of randomness depending on the volatility, but drifts towards the average of 5%. The drift at each point is determined by how far off the rate at that point is from the mean, and, of course, the value of the speed parameter. An even simpler explanation would be, the volatility determines the magnitude of the shocks over time, and the mean reversion mechanism then tries to fizzle it out. Also note that the speed of 0.1 means that it takes the rate about 7 years, which is log of 2 divided by 0.1, to travel half the distance between the current rate and the mean. Notice in the CIR, the volatility of the short rate is square root of rate times the input volatility, so you will need to enter a slightly higher volatility for CIR. And in the Merton model, there is no reversion, so enter smaller values to get plausible results. You might want to grab a cup before we hit the button in this one. Here is the output. Nothing should be surprising here. You have seen all the maths, and these visuals are meant to bring it home. We knew that the short rate is stochastic. It starts at the current value, and moves randomly over time. The first two charts show the mean and standard deviation of the short rate over time. Recall the approximation to half-life. Here it is, 1% to 3%, that is halfway to 5%, in about 7 years. The next chart then shows how the short rate distribution changes over time. Notice how the mean of the rate moves, and how the volatility spreads. The next chart then shows the probability of rate being negative. You can easily relate this chart to the previous 3 charts. The next section is where the short rate becomes relevant to what we care about. The spot rate, which is the integral or accumulator of short rate over the spot maturity. Remember, the short rate is the interest rate for a very short period of time, and if we compound the short rate, we get the rate over the longer period. You can see the mean and standard deviation of the spot rate by maturity here. The next section shows the current prices of the zero-coupon bonds. Although the short rate is stochastic, one can use the expectation to compute the present value of a zero-coupon bond, the price of which can then be easily transformed into a yield curve. We also give the prices of a 5-year constant maturity and a fixed maturity 20 years bond. The reason we analyze both constant and fixed maturity bonds is, if one takes a 20-year bond, it will be a 19-year bond next year. In addition, the underlying rates are moving, so it is hard to visualize the impact of each. The constant maturity bond has the same maturity over time, so it isolates the impact of the dynamics of the short rate. The 20-year bond then is easy to study. We then plot the distributions of the prices of these two bonds over time. The distributions are similar in a sense to the distribution of the short rate we plotted in the first section. However, as the bond prices show wider variation, we plot each distribution separately as it is difficult to make them fit to one scale. We don't have a quiz in this video, as the demo was a bit long. You may want to practice with all 3 models now, and we wish you a happy interaction with QuantPy.